Hey, Dr. Clark coming back at you with another preview video, this time section 4.4, undetermined coefficients and superposition. Now in this section, we're going to push further out of homogeneous into the non-homogeneous. We're going to stay with constant coefficient linear differential equations, but we're going to upgrade from only being able to solve homogeneous to being able to solve non-homogeneous. And so what that basically means is instead of having equals 0, we have right-hand side some function, but that function is going to be only in terms of the independent variable x. Everything else is linear and still constant coefficient. Okay, now typically when you're solving a problem like this, if you were doing as a model, it would be representing some sort of external or outside force on the system. So the simplest example is if this was a second order linear and you were modeling, say, a spring mass problem, then this external force might be some external force on the spring, pushing the spring one way or another kind of thing. All right, so what do we do? And so here's exactly that example, the forced harmonic oscillator. Here's a second order linear constant coefficient, second derivative here, that's your acceleration. This is your friction term and then your spring force, for example. And so what you might have is some time-dependent external force. So maybe there's a fan that pushes the mass one way or another, or a magnet that draws it in. So some external thing forcing the mass, that's called a forced harmonic oscillator. Now, this g of t term we call the forcing term, okay? And again, it's time dependent. So it could be constant force. For example, if the mass is hanging under gravity, then you might have a constant gravitational force or something like that. But it has to be time dependent, not depending on the position y. All right, and how would you solve this? So this is basically the idea of superposition we've learned already. If you have a homogeneous problem, then you know for second order that has two solutions, two linearly independent solutions, C1y1, C2y2. So if you had a forced problem, you could ignore the forcing, set it equal to 0, solve the homogeneous problem, and find the general solution to the homogeneous problem. Now what we need to do is solve the actual problem, okay? And so we called this a particular solution, so you just need any one solution to the non-homogeneous problem will be good enough. So we call that the particular solution, yp. And so the general solution to the fully non-homogeneous problem will be the sum of the homogeneous solution and any one particular solution to the full problem. Okay, so we've already learned how to solve this problem and get the homogeneous solution. What we need to do is figure out how do you find any one will do particular solution, and then when you combine those two together, you get the general solution to the non-homogeneous problem. All right, and that's a good question. So how do you find yp? We know how to find yh, the homogeneous problem, or the homogeneous solution. How do you find yp, the particular solution to the full non-homogeneous problem? Well, that's what we're going to learn in class. So we'll see you in class. I look forward to it. And we're going to learn how to find some particular solutions. We already know how to do the homogeneous. We'll add those together. And boom, we've got general solutions to non-homogeneous problems, at least for linear constant coefficient differential equations. So we'll see you in class.